I'll just have this here. Okay, so hello, I am Max Polosky of the AMER group, and today, as you heard, I'm going to briefly talk about Supplementary Cementitious Materials, or SCMs for short. More specifically, we're going to talk about what we know about them currently, and then what we hope to investigate about them in our new lab in the near future. So, before we start, I must define some vocabulary terms. So first of all, supplementary cementitious materials, or SCMs. These materials are any materials that can be used to substitute cement in concrete, also changing the properties of concrete at the same time. They are now very common in the construction industry to manipulate the emissions, the strength, and workability of concrete. So why are these important? Well, after water, concrete is the second most used material on the entire Earth. The main constituent of concrete is cement, and the production of cement takes a lot of energy. In fact, the cement industry is responsible for up to 8% of all carbon emissions on the planet. So every piece of infrastructure we build using cement instead of replacing cement contributes to global warming. Second, I will define Portland cement. Portland cement is the most used kind of cement, the most conventional cement, and it is combined usually with aggregates of sand and gravel or crushed stones to create concrete. It is used in most modern construction projects. Third, I'll define cementitious. So cementitious describes any materials that react similarly to cement, creating a strong compound called CSH, as you can see there, which is integral to concrete strength, but also creating a byproduct called CH, which is weaker, which is where the next term, pozzolanic, comes in. Pozzolanic materials are materials that take the weaker product of cementitious reactions, CH, and convert them into the stronger compound, CSH, which gives concrete its strength. So with these in mind, I will talk about some common industry supplementary cementitious materials currently. So first of all, we have fly ash, which is a fine powder-like substance which is produced as a byproduct when we burn coal. And it can replace about 30% in weight of Portland cement. Now, there are two types of fly ash that are commonly used as an SCM. First is Class C fly ash, which contains higher calcium concentration and has cementitious properties, and it's able to replace about 20 to 35% of cement in weight. The second type of fly ash is fly ash Class F, which is actually a pozzolan, mainly consisting of alumina and silica, meaning it can replace only about 15 to 25% of cement in weight. And while many parts of the world, like Poland, for example, rely heavily on coal for now, so we have a lot of fly ash, as coal use is being reduced, then that reduces the effectiveness or the use of fly ash in the future. Another common SCM is called slag, which is a byproduct of smelting metals and ores, and is commonly used in Portland cement with about 20 to 50% weight replacement. And slag has a very high potential for carbon capture, with about 0.27 to 0.43 kilograms of carbon dioxide being stored in slag cement per kilogram of concrete. Another common SCM is silica fume, which is a byproduct of reducing quartz in electric arc furnaces, basically to manufacture silicon metals used in everyday items like solar panels or technologies like phones, computers, etc. Silica fume is a very pozzolanic material. It can replace cement in about 5 to 10% weight, and it is also typically added to concrete to decrease the permeability of concrete and overall increase the resistance to corrosion of our concrete, which of course makes it stronger and lasts for longer. Another common SCM is off-spec glass fibers. So glass fibers that customers don't want to use can instead be used to replace cement in concrete, up to 20% in weight replacement, without many changes to the properties of the concrete. And on top of this, adding glass fibers improves the durability and resistance of the concrete against alkali silica reactions, which are reactions that degrade our concrete over time, which we don't want, of course. Another more unusual SCM is called flash graphene. It is produced through flash joule heating, basically lots of electricity through a carbon-containing material, such as plastic, rubber tires, coffee beans, any material with carbon in it. And in flash joule heating, a quick electrical charge is put through these items where we can get the carbon out and also get rid of any material that isn't carbon from those materials. And adding about 0.035% weight in concrete of the flash graphene increases the compressive strength of the cement and of the concrete by up to 30%, which is, really amazing. Also, adding this flash graphene encourages the formation of the strong compound here, CSH. So in the future, there are still many potential SCMs that we want to investigate. Many good SCMs, which are ones that will replace more cement, and these all have common characteristics. First of all, they must have silica or alumina to strengthen the concrete, and second of all, the silica and alumina should be in a non-crystalline form, making it, easier to react and create the CSH compound that we want. And so, besides the ones that I mentioned here, we could look at SCMs such as rice husk ash, sugarcane ash, and tire-derived fuel ash. Another very promising alternative to SCMs is geopolymers. Geopolymers, in theory, can completely replace cement in concrete if a very basic solution is mixed with a source material containing alumina and silica in a certain way. And for this reason, that is being researched very heavily. But the reason this is not used is because very basic solutions are difficult to use on job sites. And so geopolymers are suboptimal for large construction projects. So in conclusion, with our new lab space being close to completion, we'll soon be able to start working with these things and getting our hands dirty. So stay tuned for our next talk. We'll hopefully have some more insightful data on these important materials and be further on a mission towards greener and more efficient construction materials. And last thing I would like to do is, of course, thank the many people who helped in this project, such as our group advisor, Dr. Emmer, who has been amazing, answering all of our questions and working with us to get our new lab set up, all while in a different time zone. That must be a lot of hard work. And I would also like to thank the whole Emmer group, everyone in it. I hope we thrive in our new lab environment. And finally, I'd like to thank ASDRP as a whole for giving us this very wonderful opportunity to conduct actually meaningful research while in high school. For me, this has been a very eye-opening experience. And so thanks everyone also for listening to our short talk, and we hope to see you soon.